All right, we're ready to pick up our proof where we left off in the previous video. And to refresh your memory here, we again have our main proof tree. We've split it up into some pieces here. So there's the GCD tree where this if-then and initialization phase was split out from the while loop, which is what we're going to tackle next. And then below here was the proof tree for the while loop. And so we pop back up here. This is the component that we would now like to work with. All right, so this is the T init tree. All right, and so this looks like a pretty clear application at this point of the rule of composition. All right, we have two statements, and so it's pretty reasonable to assume that, well, let's split these up, see what our Q condition is that's going to hold between these, and then proceed from there. All right, so what this is going to give us then is two new trees to go create. And we can give these names as well so that none of this gets too big. So here's our T init tree that we will go complete, and an if then else tree. All right, so let's make this init 2 perhaps, since how about we just call it assigns instead. So there we go. So this tree for assignments is what we will finish second, right? We're pushing things backwards through the entire tree. We have the post condition that we want, and the idea is we kind of massage this and push this through the program until we get something coming out the front as our precondition, and expect that to line up with what we intended the precondition to be. So that means we're going to start working with the if then else tree here. All right, and so we need to break this up into a few pieces, right? And so if you recall, our condition on the if then else is m greater than n, and if that's true, I gets the value n, else I gets the value m. And our loop condition loop invariant holds at the end. So this is going to split into two components, right? So if we think of the then clause, then Q will hold, as will the condition m greater than n, in which case we do I set equal to n and expect the loop invariant to hold. The other one that we need to show is that if Q and not m greater than n holds, and we do I set equal to m, again our loop invariant should hold after that. And then this is just a application of the condition rule. All right, so at this point we could plow ahead and see what to do on the else clause. All right, so we could pick either of these first, but we'll pick the else clause first. So that's our bit over here. All right, so we'll give these names as well so we can glue these together. So here's our then tree, and this will be our else tree. All right, oops, the else one here. Right, so if we want to work with the else tree, right, then the first thing we might think about is doing something with the axiom of assignment here, right? So we have an assignment statement, so that's the obvious thing to do. So let's fill in our loop invariant, right? So we can bounce back up here to the top where we have these abbreviations, and we'll copy this back down, right? And so our loop invariant again is that every value greater than I is not a common divisor. And so if we have I set equal to m here, right, then we know that we need to replace the value we're assigning to with that with the expression, right? So in this case, I just appears here, and so this is what we get as our new Hoare triple that we create using the axiom of assignment. All right, and so that looks good, except that this, of course, doesn't quite match up with what we have here, right? So our precondition is something q to be determined and not m greater than n, and so that doesn't match our precondition. So that tells us that, well, we're not really ready for this axiom of assignment. All right, this is sort of our exploratory step, if you will, and say, okay, we're not quite ready for that. We're pretty sure we're going to need it. Maybe there's an application of the rule of consequence. All right, so we can see that perhaps there is some q and not m greater than n, right, that implies this precondition, right? For all j greater than m, it's not a common divisor. All right. So what do we think of that? Is this something we think would hold? So what might q be? Right? So what about this statement here? For all j greater than m, we want this to hold. All right. So this is pretty straightforward. We're going to pause here for a second. Something just came up, and I'll pick this up in just a minute.